Hi students, as you know, NDA has introduced a new unit in the chemistry syllabus for both the NEET and JEE from the year 2024 onwards. The new unit included is the principles related to practical chemistry. Since it is a newly introduced topic, the necessary study materials may not be available in print and visual media. But you need not worry. I am uploading video classes through my YouTube channel explaining the theory related to chemistry practical, which include a lot of multiple choice questions and their well explained answers. By the way, I am Dr. Siriak Matthew, a retired associate professor in chemistry. The purpose of my channel, Chemistry Master, is to upload video classes related to topics in chemistry within secondary, undergraduate, and postgraduate levels. At present, I am uploading video classes related to NEET, JEE Main and Advanced, and other entrance examinations. There will be a set of video classes for each chapter. In the present set of videos, we discuss the principles related to practical chemistry. This set includes 6 video classes. The first one, titled as Principles Related to Practical Chemistry, Part 1A, explained detection of extra elements and detection of functional groups. The second, titled as Principles Related to Practical Chemistry, Part 1B, contains multiple choice questions related to Part 1A. Part 2 explains preparation of some organic and inorganic compounds and a titrimetric analysis. Part 3, qualitative analysis for anions, and Part 4, qualitative analysis for cations. The Part 5 explains some physical chemistry experiments. At the end of each part, multiple choice questions related to that part are explained. Even if you go through a handbook of chemistry practical several times, you may not be able to remember the experiments and the theory behind it. But an audiovisual presentation will catch your attention. That is why I have introduced a lot of animations in these video classes so that you will get a feel of doing the experiments in the laboratory. However, animations never represent the real situation. And this is not an instruction manual for doing the experiments in the lab. The main purpose is to make you understand the theory behind the experiments. In the laboratory, you have to take several precautionary measures while doing the experiments. For your convenience, I have introduced video chapters or timestamps in the description part of the videos. This will help you to watch and rewatch separately the different topics explained in a particular video. The links for other videos are also given in the description part. You can easily move to any of these 6 videos using these links. I hope these video classes will definitely help you to understand the theory behind the experiments. If you like the video, please subscribe my channel and forward to others. You can expect similar video classes from other chapters of Class 11 and Class 12 Chemistry soon. Let us begin with part 1 of this series of video classes. We start with detection of extra elements in a given organic compound. Most commonly occurring elements in organic compounds are carbon, hydrogen, nitrogen, sulfur, and halogens such as chlorine, bromine, and iodine. Less common elements that may be present are phosphorus, arsenic, antimony, or other metals which may be present as salts of organic acids. As you have studied, carbon and hydrogen are detected by heating the compound with copper oxide. Carbon present in the compound is oxidized to carbon dioxide, tested with lime water, which develops turbidity. The hydrogen present will be converted to water, tested with anhydrous copper sulfate, which turns blue. There is no direct method to detect the presence of oxygen. Common elements other than carbon, hydrogen, and oxygen that are present in an organic compound are known as extra elements. These are nitrogen, sulfur, and halogens, mainly chlorine, bromine, and iodine. In order to detect nitrogen, sulfur, and halogens, it is necessary to convert them into ionizable organic substances so that inorganic qualitative methods of analysis can be applied. This conversion may be accomplished by several methods, but the best procedure is to fuse the organic compound with metallic sodium. The method was introduced by J.N. Lassine in 1843 and is known as the Lassine's test. Let us see how Lassine's test is conducted. Compared to inorganic compounds, the atoms in an organic compound are linked to each other by covalent bonds. Therefore, organic compounds do not furnish ions in solution. Therefore, in order to test the presence of the above elements in an organic compound, it is fused with a sodium metal to form ionizable sodium salts. We can also use potassium for fusion, but sodium is preferred because it is easily available and its reaction is controllable compared to potassium. When an organic compound is heated with the sodium metal, nitrogen, if present, will be converted to cyanide ions. Sulfur, if present, to sulfide ions, and halogens, if present, to halide ions. By halogen, we mean chlorine, bromine, and iodine. When fused, carbon present in the organic compound combines with the nitrogen, giving sodium cyanide. Sulfur, if present, combines with the sodium, giving sodium sulfide, and similarly, halogens gives sodium halide. Sometimes the organic compound may contain nitrogen and sulfur together. In such case, if you do not use enough sodium, sodium thiocyanate will be formed. First, we cut a small piece of sodium, clean it, and introduce it into the ignition tube. Ignition tube is a small glass tube, a thin glass tube. It is also called a fusion tube. So a small piece of uh, sodium is placed at the bottom of the tube. Now melt the metal by gently heating the ignition tube in the flame. Cool the ignition tube and then add a pinch of the organic compound into the ignition tube so as to cover the sodium metal completely with the organic compound. Now heat the ignition tube gently in the flame. Continue heating so that the ignition tube becomes red hot. Now drop the ignition tube quickly into the china dish containing about 15 ml distilled water. The tube breaks. The process is repeated 2 or 3 times so that sufficient concentration of the sodium salt is obtained. Boil the content of the china dish for about 10 minutes and then filter the solution. The filtrate obtained is called Lassine's extract or sodium extract. The extract will be alkaline due to the reaction of unreacted sodium with water. The rest of the tests are carried out using this extract. First, we test the presence of nitrogen. For that, the sodium fusion extract is boiled with parasulfate and then acidified with a dilute sulfuric acid. The formation of Prussian blue color confirms the presence of nitrogen. This is the extract that we have prepared. We keep it in a boiling tube and that is used as the stock solution. This is parasulfate solution and it is prepared freshly. In a test tube, we take about 1 ml of the Lascine's extract and an equal volume of parasulfate solution. Now boil the solution for some time. When boiled, sodium cyanide first reacts with the parasulfate and sodium hexacyanidopherrate is formed. And this is sodium hexacyanidopherrate. Now we cool the solution and to that add a few drops of dilute sulfuric acid. When dilute sulfuric acid is added, a Prussian blue color appears. And this is the Prussian blue color. When acidified with the sulfuric acid, some ferrous ions are oxidized to ferric ions. FeSO4, sulfuric acid, ferric sulfate. The ferric ions present react with the sodium hexacyanidopherrate to produce iron 3 hexacyanidopherrate, ferriferrocyanide. And this iron 3 hexacyanidopherrate shows the Prussian blue color, an intense blue color. Sodium hexacyanidopherrate, now the ferric sulfate, then this is the Prussian blue. This complex gives the Prussian blue color. Sometimes we add ferric chloride solution so as to obtain a clear Prussian blue color. Next, we test the presence of sulfur when nitrogen is not present. The sodium sulfide formed due to the presence of sulfur in the organic compound can be tested by any of the following tests. The first one is the Lascine's extract is acidified with acetic acid and then treated with a lead acetate solution. The formation of a black precipitate indicates the presence of sulfur. Second test is to the Lascine's extract, we add sodium nitroprusside. If a purple-violet coloration appears, that shows the presence of sulfur. This is the Lascine's extract. We take about 1 ml of the extract in a test tube. First, we acidify the solution with acetic acid. We add a few drops of acetic acid into the solution. After that, we add lead acetate solution. A few drops of lead acetate solution we are adding. And we use a dropper for that. So the black color appears. And this black color is due to the formation of lead sulfide. Lead sulfide is black in color. The ionic reaction can be represented like this. S2 minus ions, lead 2 plus giving lead sulfide. Now let us see the second test. Again, we take another quantity of the Lascine's extract in a test tube. About 1 ml is enough. And this compound is sodium nitroprusside. We add a few drops of sodium nitroprusside using a dropper. Now, thus a violet color appears. And this purple violet color is due to the formation of sodium thionitroprusside. Sodium nitroprusside is this compound. It combines the sodium sulfide, giving sodium thionitroprusside. And this sodium thionitroprusside is having a purple violet color. The ionic reaction is given by this equation. S2 minus, this is the complex ion, and this ion is responsible for the purple violet color. Sometimes the organic compound contain sulfur and nitrogen together. If nitrogen and sulfur are present together in an organic compound, sodium thiocyanate will be formed. It gives a blood red color with ferric ions, and no Prussian blue color is obtained. And that is because there may not be any free cyanide ions. So, if the compound contains nitrogen and sulfur together, when fused with the sodium, it is converted to sodium thiocyanate, NaSCN. When we add ferric chloride or ferric ions, this thiocyanate combines with these ferric ions, giving ferric thiocyanate. And this ferric thiocyanate is blood red in color or intense red. And if you get a blood red color, that shows the presence of both nitrogen and sulfur in the organic compound. So sodium thiocyanate, we take about 1 ml of the extract. To that, we are going to add ferric chloride solution. Using a dropper, we add a few drops of ferric chloride. So this intense red color is formed. And this color is known as the blood red color. When excess sodium is used, the sodium thiocyanate will decompose. If sodium fusion is carried out with excess of sodium, the thiocyanate decomposes, giving sodium cyanide and sodium sulfide. Now we can test the presence of nitrogen and sulfur independently. So for testing nitrogen, to one portion of this solution, we add ferrous sulfate and sulfuric acid, and we expect the formation of Prussian blue. But one difficulty arises in this case. You may not get the Prussian blue color at first. This is because when ferrous sulfate is added, ferrous sulfide precipitates, which is black in color. If you boil the solution and acidify with the dilute sulfuric acid, the ferrous sulfide dissolves and the Prussian blue color appears. For testing sulfur to another sample, we add acetic acid and a lead acetate solution. And the black precipitate shows the presence of sulfur. Next is the test for halogens. By halogen we mean chlorine, bromine and iodine. If sulfur and nitrogen are absent, we acidify a small amount of the extract with the nitric acid and add excess of silver nitrate solution. If a white precipitate soluble in ammonium hydroxide formed, it shows the presence of chlorine. A pale yellowish precipitate partially soluble in ammonium hydroxide shows the presence of bromine. Yellow precipitate insoluble in ammonium hydroxide shows the presence of iodine. Sodium halide, when we heat with the sodium, we get sodium halide. Well, we treat it with the silver nitrate, then we get the silver halide. Here X is either chlorine, bromine, or iodine. This is leucine's extract. We take about 1 ml of leucine's extract in a test tube. First, we acidify it with dilute nitric acid. Using a dropper, we add a few drops of dilute nitric acid to the leucine's extract taken. After that, we add a few drops of silver nitrate solution. This is silver nitrate solution. And again, we are using a dropper to add a few drops of silver nitrate solution. So a curdy white precipitate is formed here. And this indicates the formation of silver chloride, and that shows the presence of chlorine. If a pale yellow precipitate is formed, that shows the formation of silver bromide. And an yellow precipitate shows the presence of silver iodide. Now, we can distinguish these three by adding ammonium hydroxide. We add ammonium hydroxide to first this silver chloride precipitate. Using a dropper, we add a few drops. So the precipitate dissolves completely. So if silver chloride is formed, it completely dissolves in ammonium hydroxide. That shows the presence of chlorine. If we add ammonium hydroxide to the second precipitate, it dissolves only partially. So some of the precipitate remain undissolved. And that shows the presence of bromine. Now we are adding ammonium hydroxide to the third test tube, but it remains insoluble. That shows the presence of iodine. The test for halogens must be modified if sulfur or nitrogen or both are present. If nitrogen or sulfur is also present in the organic compound, the sodium fusion extract is first boiled with concentrated nitric acid to decompose cyanide or sulfide of sodium formed during Leucine's test. These ions would otherwise interfere with the silver nitrate test for halogens. So sodium cyanide is present when heated with the nitric acid. It is converted to hydrogen cyanide and will escape from the solution. Similarly, when boiled with the nitric acid, sodium sulfide, if present, will be converted to hydrogen sulfide, and that also will be escaping from the solution. If we do not remove these ions, they form a white precipitate of silver cyanide and a black precipitate of silver sulfide respectively, thereby interfering in the silver nitrate test for halogens. Sodium cyanide plus silver nitrate, sodium nitrate from silver cyanide, and the silver cyanide forms a white precipitate. Similarly, sodium sulfide reacts with the silver nitrate giving silver sulfide, that is a black precipitate. So we do not get the white precipitate or pale yellow precipitate when silver nitrate is added. Another test for halogen is the layer test. This is mainly done for iodine and bromine. If we get positive silver nitrate test, that shows the presence of halogens in the compound. But which halogen is indicated is confirmed by the layer test. Acidify about 1 ml of the sodium fusion extract with a dilute sulfuric acid, cool it, and add 1 ml carbon tetrachloride. Then add chlorine water dropwise with vigorous stirring or shaking. If iodine is present, the organic layer changes to purple color. If bromine is present, the organic layer becomes reddish brown. If chlorine is present, no color change is observed. Chlorine can displace bromine and iodide ions from their aqueous solution as shown below. So chlorine, so if it is KBr and from the aqueous solution chlorine displaces bromine. Then similarly from the potassium iodide, if we consider potassium iodide, iodine is displaced. Bromine and iodine are soluble in carbon tetrachloride and hence can easily identified from the color of the solution. So we take about 1 ml of the lysines extract. This is lysines extract. We add a few drops of dilute sulfuric acid using a dropper. After that, we add about 1 ml of carbon tetrachloride to this solution. That also we do it using a dropper. And we know that carbon tetrachloride is immiscible with water. So two layers will be formed. The bottom layer will be the carbon tetrachloride and the upper layer is the aqueous layer. Now we are going to add chlorine water to this solution. Again, using a dropper, we add some chlorine water to this solution taken in the boiling tube. Now we have to shake the solution well. For that, we close it using a cork and it is thoroughly shaken. So, if iodine is present, a violet color is observed for the carbon tetrachloride layer or organic layer. And the aqueous layer will be almost a clear solution. This is because iodine is soluble in organic layer but not in the aqueous layer. Similarly, if we get a red color that shows the presence of bromine. Here the aqueous layer also is slightly colored because bromine is slightly soluble in water. And no color change. That shows the presence of chlorine. Next, we shall study the test for detection of certain functional groups that may be present in an organic compound. We need study only a few functional groups such as hydroxyl, alcoholic and phenolic, carbonyl, aldehydes and ketones, carboxyl and amino group. First, we consider the test for alcoholic group. Alcohols react with the metallic sodium and liberate hydrogen gas. To a little of this substance, in a dry test tube, a small piece of metallic sodium is added. If the given substance is a liquid, it's a solid, dissolve it in dry benzene. So this is the solution of the given substance. And sodium metal. Sodium metal is kept under kerosene. So before adding sodium, the kerosene should be wiped off using a filter paper. So we take a small piece of the sodium metal and drop it into the solution. And we will observe the formation of bubbles. These bubbles are due to the liberation of hydrogen gas. So the alcohol reacts with the metallic sodium, we get RONA plus hydrogen gas. This hydrogen gas is liberated in the form of bubbles that shows brisk effervescence. Phenol also answer this test. So phenol plus sodium phenoxide, and hydrogen gas is liberated. And this is a simple test for the presence of hydroxyl group. Another test is acetylation test. A little of this substance is heated with a glacial acetic acid and a few drops of concentrated sulfuric acid. The solution is cooled and it is poured into excess of water containing in a beaker. So the given substance, if it is a liquid, we take about 1 ml, and this is glacial acetic acid. We add a few drops of glacial acetic acid to the solution. It is followed by a few drops of concentrated sulfuric acid. By means of a dropper, we are adding some concentrated sulfuric acid to this solution. Now we boil the solution or heat the solution in a water bath. After warming, it is cooled and it is poured into a beaker containing water. It is stirred well, and if you smell it, a sweet or pleasant fruity smell is observed. Then alcohol reacts with the acetic acid, giving the ester. This is the ester form, and ester formation takes place in an acidic medium. An example is ethanol plus acetic acid giving ethyl acetate, and this ethyl acetate is having the pleasant fruity smell. Phenol also form esters, but the ester will have a phenolic odor. So here we get phenyl acetate. Another test is test with cerebric ammonium nitrate. Alcoholic compounds on reaction with cerebric ammonium nitrate give a red coloration due to the formation of a complex. This is cerebric ammonium nitrate alcohol, and this complex is having a red color. We take about 1 ml of the solution of the given substance. If it is a solid, we make a solution a suitable solvent. And this is cerebric ammonium nitrate. We add a few drops of cerebric ammonium nitrate to this solution using a dropper. Appearance of red color, almost a red color, that shows the presence of hydroxyl group. An example is if you take ethanol, and this is the complex that is formed, and this complex shows red color. Phenol also forms a complex but gives a brown or black color. It may not be red. So we take phenol, and this is the complex that is formed, and the color will be either brown or black. Another test for alcohols is the Lucas test. Lucas test is mainly used to distinguish between primary, secondary, and tertiary alcohols. Lucas reagent contains zinc chloride and concentrated HCl. The reagent reacts with primary, secondary, and tertiary alcohols at different rates. Tertiary alcohols react almost instantaneously. Secondary reacts in about 1 to 5 minutes, and primary alcohols reacts very slowly. At a room temperature, there may not be any reaction at all. Suppose that we take 3 samples. So this test tube contains a primary alcohol, and this is a secondary alcohol, this one a tertiary alcohol, and this is a Lucas reagent. By means of a dropper, we are adding this Lucas reagent to these 3 test tubes. First, I have added to the primary, then to the secondary, and finally to the tertiary. In the case of tertiary, a turbidity appears immediately. And for secondary alcohol, the turbidity will be obtained after 2 to 5 minutes. But for the primary, it takes a long time. So tertiary, we get turbidity immediately. For secondary, within 2 to 5 minutes. And for primary, long time after heating. So a primary alcohol react with zinc chloride and HCl. Zinc chloride and HCl is the Lucas reagent. We get a primary alkyl halide. The reaction is very slow. A secondary alcohol, this is a secondary alcohol, it reacts with the zinc chloride giving a secondary alkyl halide. And the reaction is much faster compared to the first one. So this is a tertiary alcohol that reacts with the zinc chloride, and a tertiary alkyl halide is formed. One condition is that the alcohol must be soluble in Lucas reagent. The alkyl halides formed are insoluble. That is why we observe the turbidity. The turbidity or another layer is due to the presence of these alkyl halides. Another important test for alcohols is the iodophone test. Iodophone test is answered by the following 4 groups of organic compounds. Ethanol answers iodophone test. Secondary alcohols like CH3, CHOH, or where R is alkyl or aryl. Then methyl ketones answer iodophone test. Acetaldehyde shows as iodophone test. To carry out the reaction, potassium iodide and a sodium hypochlorite solution are added to the compound in presence of sodium hydroxide solution. So, to about 0.2 ml of the given compound, add 10 ml of 10% aqueous potassium iodide solution and 10 ml of freshly prepared sodium hypochlorite solution. Gently warm the solution and yellow crystals of iodoform separates. So this is the given substance, and 10% potassium iodide solution, and this is a freshly prepared solution of sodium hypochlorite. First we add about 10 ml of this potassium iodide solution. After that, we are adding 10 ml of sodium hypochlorite solution. Now, we want the solution in a water bath. And we remove it from the water bath, allow it to cool, and yellow crystals of, pale yellow crystals of iodoform separates. Now let us see how this reaction is taking place. Sodium hypochlorite first oxidizes potassium iodide to potassium hypoiodide, which then oxidizes the ethanol to acetaldehyde. The hypoiodide then iodinate acetaldehyde to triiodoacetaldehyde. Aqueous sodium hypochlorite always contains sodium hydroxide, and it converts the triiodoacetaldehyde into iodoform. Let us see the reactions. First, the potassium iodide, then this is sodium hypochlorite. It is converted to potassium hypoiodide. Potassium hypoiodide. So if we take ethanol as an example, this potassium hypoiodide oxidizes ethanol to acetaldehyde first. And after that, it iodinates acetaldehyde so that triiodoacetaldehyde is formed. Now, this sodium hypochlorite solution always contains sodium hydroxide, and a reaction with the sodium hydroxide, this iodoform separates. Another method to prepare iodoform is using sodium hydroxide and iodine solution. To 1 ml of the given substance, we add 2 ml of 5% solution of sodium hydroxide. If the given substance is a solid, we dissolve it in water or dioxide. Now we add potassium iodide iodine reagent till the dark color of iodine persists. So we take about 1 ml of the given substance, and we have 5% sodium hydroxide solution, and this is potassium iodide iodine reagent. First we add sodium hydroxide dropwise, and after that we add the potassium iodide iodine reagent, and we want the solution in a water bath. We add enough potassium iodide iodine reagent till the brown color of iodine persists. Removing from the water bath, cool it, the crystals of iodoform separates. The reaction can be represented in this way, and this is the given alcohol. It reacts with iodine and it is converted to the ketone. So with the excess of iodine and sodium hydroxide, we get this compound, and along with that, iodoform is produced. The potassium iodide iodine reagent, and this is prepared by dissolving 20 gram of potassium iodide and 10 gram of iodine in 100 ml water. Next, we shall study the test for phenolic group. In phenols, the hydroxyl group is directly attached to the carbon in an aromatic ring. Phenols are weakly acidic. Therefore, they are soluble in sodium hydroxide solution. but at the same time, they are not sufficiently acidic to be soluble in sodium hydrogen carbonate solution. First is the neutral ferric chloride test. Phenol gives colored complex with a neutral ferric chloride solution. And this is ferric chloride solution. First, let us see how neutral ferric chloride is prepared. For that, we need sodium hydroxide solution. So, little about 1 ml of the ferric chloride is taken, and to that we are adding dilute sodium hydroxide solution drop by drop. And the addition continues till a small but permanent brown precipitate appears. So we are adding sodium hydroxide drop by drop. And addition is continued till a brown precipitate is formed. So at this point, we stop addition. Now we filter this solution and a clear solution is obtained. Now, this is the phenol. About 1 ml of phenol is taken, and to that we are adding this ferric chloride solution. A few drops of neutral ferric chloride solution. A violet color appears, and the presence of this violet color shows the presence of phenol. So phenol reacts with the ferric chloride and it gives this compound. The violet color is due to the formation of this complex. Another important test for phenolic group is the phthalate dye test. And the phthalate dye test is carried out in the following way. To about 0.1 gram of the organic compound, we add 0.1 gram phthalic anhydride in a dry test tube. Now, 2 or 3 drops of concentrated sulfuric acid is added and heated it in an oil bath. It is then cooled and the mixture is poured into 15 ml dilute sodium hydroxide solution. A pink color appears which shows the presence of phenol. So this is, suppose we are taking phenol, about a 0.1 gram of phenol, and this is phthalic anhydride and a concentrated sulfuric acid. And we add a pinch of phthalic anhydride into the phenol taken, followed by few drops of concentrated sulfuric acid. Now we heat this mixture in an oil bath for some time. After that, we remove it from the oil bath and we take sodium hydroxide solution in another beaker and we pour the solution content of the test tube into the sodium hydroxide solution. The pink color appears, and this pink color is due to the formation of phenolphthalein. If we use phenol, we get the pink color. Instead of phenol, if we are using orthocresol, the color obtained will be red. Metacresol will give a bluish purple color, and a paracresol, no color is observed. The chemical reactions that take place in phthalate dye test is as follows. This is phenol and this is phthalic anhydride. When we heat it with the concentrated sulfuric acid, this is formed. And with the sodium hydroxide, the ring breaks and a quinonoid structure is formed. And this is the phenolphthalein in alkaline medium. And this compound shows pink color. and the pH range will be 8.3 to 10. If you use excess of sodium hydroxide, it becomes colorless because phenolphthalein becomes colorless if the pH is greater than 12. Next, we will consider aldehydic and ketonic groups. Both aldehyde and ketones contain carbonyl groups and are commonly known as carbonyl compounds. Identification of aldehydes and ketones is done by two important reactions of carbonyl group. One, addition reaction of on double bond of C double bond O group and oxidation of carbonyl group. Addition reactions of derivatives of ammonia are important from the point of view of identification of carbonyl compounds. So, aldehyde or ketone, the carbonyl group, derivative of ammonia, for example, RNS2, we get this unsaturated and usually this is colored or maybe alkyl, aryl or C6H5NH etc. These reactions are catalyzed by an acid or a base and do not occur under strongly acidic or basic conditions. Each reaction requires an optimum pH for its occurrence. Therefore, maintenance of pH is very important in while carrying out these reactions. First, let us consider oxidation of aldehydes and ketones. Aldehydes are easily oxidized to carboxylic acids, but ketone requires relatively stronger oxidizing agent. This difference in reactivity can be utilized to distinguish between these two functional groups. Mild oxidizing agents that can be used for aldehydes are 1. Tollens reagent, 2. Fehling's reagent, 3. Benedict's reagent. Ketones do not reduce these reagents. Fehling's and Benedict's reagents are alkaline solutions containing cupric ions complexed with a tartrate and citrate ions respectively. Tollens reagent is alkaline solution containing silver ions complexed with ammonia. This is the complex. Fehling's reagent is alkaline solution containing cupric ions complexed with tartrate ions. Fehling's reagent consists of Fehling solution A, which is aqueous copper sulfate solution, and a Fehling solution B, which is alkaline solution of sodium potassium tartrate. These two are taken as a 1:1 mixture. Benedict's reagent is alkaline solution containing cupric ions complexed with citrate, that is copper sulfate plus sodium citrate. The following test is answered by both aldehydes and ketones. That is 2,4-dinitrophenylhydrazine test or 2,4-DNP test. This reagent is prepared by dissolving dinitrophenylhydrazine in alcohol and adding little concentrated sulfuric acid. It is also called a Borchers reagent. Dissolve the organic compound in alcohol and add a few drops of 2,4-dinitrophenylhydrazine and shake well. So, the organic compound that is dissolved in alcohol. This is 2,4-DNP, 2,4-dinitrophenylhydrazine. We are adding a few drops of 2,4-DNP to the solution of the organic compound in alcohol. Now we close the test tube using a cork and it is vigorously shaken. So appearance of yellow, orange or orange red precipitate shows the presence of either aldehyde or ketone. And the orange red precipitate is due to the formation of 2,4-dinitrophenylhydrazone. Once again, I remind you that animations never exhibit the true experimental situation, but helps to understand the theory behind it. Common aromatic as well as aliphatic aldehydes and ketones will answer this test. The following tests are answered by aldehydes only. One is Schiff's test. Schiff's reagent is prepared by dissolving para-rosanilin hydrochloride in water and decolorizing the solution by passing sulfur dioxide. To a solution of the organic compound in alcohol, we add a few drops of Schiff's reagent. If the given compound is a liquid, we need only 2 or 3 drops of the given compound. A pink color appears. So this is the given organic compound, and a Schiff's reagent, we are adding a few drops of Schiff's reagent to this solution. So a pink color appears. But this pink color shows the presence of aldehyde. Once again, this test is answered by aldehydes only. Next test is Felling's test. As I said earlier, Felling's reagent is a 1:1 mixture of Felling solution A and Felling solution B. Felling solution A is aqueous copper sulfate solution, while Felling solution B is an alkaline solution of sodium potassium tartrate. Felling's reagent is freshly prepared by mixing equal amounts of Felling solutions A and B. This is because Felling's reagent deteriorates on keeping, while Felling solution A and B are quite stable. Cupric ions form a complex with the tartrate ions. Due to complex formation, Cu2 plus ions are not precipitated as cupric hydroxide. The reagent oxidizes aldehydes while ketone remains unaffected. The copper ions are reduced to Cu plus ions. However, aromatic aldehydes do not show positive Felling test. For doing the Felling's test, we take 1 ml each of Felling solution A and a Felling solution B in a dry test tube and add 2-3 drops of the liquid compound and heat for 2 minutes on a water bath. If the given compound is a solid, dissolve it in alcohol. Appearance of brick red precipitate or cuprous oxide shows the presence of aldehyde. So the organic compound, this is the Felling solution A, Felling solution B. First we take 1 ml of Felling solution A. To that we are adding 1 ml of Felling solution B. Mix it well, and to this solution we add a few drops of the given organic compound using a dropper. Now we heat the solution or the test tube in a water bath. Next, we will consider aldehydic and ketonic groups. Both aldehyde and ketones contain carbonyl groups and are commonly known as carbonyl compounds. Identification of aldehydes and ketones is done by two important reactions of carbonyl group. One, addition reaction of on double bond of C double bond O group and oxidation of carbonyl group. Addition reactions of derivatives of ammonia are important from the point of view of identification of carbonyl compounds. So, aldehyde or ketone, the carbonyl group, derivative of ammonia, for example, RNS2, we get this unsaturated and usually this is colored. R may be alkyl, aryl, or C6H5NH, etc. These reactions are catalyzed by an acid or a base and do not occur under strongly acidic or basic conditions. Each reaction requires an optimum pH for its occurrence. Therefore, maintenance of pH is very important in while carrying out these reactions. First, let us the formation of orange-red precipitate indicate the presence of aldehyde. The fourth test that is answered by aldehydes alone is the tolerance test. Tolerance reagent is ammoniacal silver nitrate solution. It is prepared in the following way. Take about 2 ml of the silver nitrate solution in a clean test tube and add 2-3 drops of dilute sodium hydroxide solution. Add ammonium hydroxide solution drop by drop till the precipitated silver oxide, which is brown in color, is almost dissolved. To the above solution, add 2-3 drops of the organic compound. If the given compound is a liquid, add 2-3 drops, and if it is a solid, dissolve it in alcohol or water. We can take 1 ml of the solution. Heat on a water bath. A layer of metallic silver forms on the inner side of the test tube. First, we prepare the tolerance reagent. For that, we take about 2 ml of the silver nitrate solution in a clean test tube. Using a dropper, we are adding sodium hydroxide solution drop by drop till a brown precipitate is formed. And brown precipitate is due to the formation of silver oxide. Now we add ammonium hydroxide drop by drop till the brown precipitate is just dissolved. Now, to this solution, we are adding the given organic compound. Now, place the test tube in a water bath. After some time, we will observe a metallic layer of silver forms on the inner side of the test tube. Hence, this test is also known as the silver mirror test. Next, we shall consider the test for carboxyl group. Carboxyl group contains both a carbonyl and a hydroxyl group. Since compounds with carboxyl groups are acidic, they turn blue litmus red and react with the sodium hydrogen carbonate solution to produce effervescence. And first let us see the litmus test. For that, place a drop of the organic compound or a drop of the solution of the compound on a moist blue litmus paper. The blue color of the litmus changes to red. It shows the presence of either carboxylic group or phenolic group. This is the organic compound, and we place a moist blue litmus paper on a white tile. Now add a drop of the given organic compound to the litmus paper. So it turns red. The second test is sodium hydrogen carbonate test. To about 2 ml of the saturated aqueous solution sodium hydrogen carbonate, we add a few drops of the liquid compound. If it is a solid, we need a few crystals of the compound. Brisk effervescence due to the evolution of carbon dioxide indicate the presence of carboxyl group. So the organic compound, this is sodium hydrogen carbonate. We take about 2 ml of sodium hydrogen carbonate in a test tube. To that, we are adding the organic compound slowly. And we will observe the formation of bubbles, and this is due to the liberation of carbon dioxide. RCOH plus sodium hydrogen carbonate, RCONA plus water and carbon dioxide. This test distinguishes carboxylic acids from phenols. Phenols are not acidic enough to react with the sodium hydrogen carbonate. Sodium hydrogen carbonate solution should be added slowly to observe the effervescence clearly. Another important test for carboxylic acid is the formation of esters when reacted with alcohols in acidic medium. To conduct the test, we take about 0.1 gram of the compound in a test tube and add 1 ml ethanol and 2-3 drops of concentrated sulfuric acid. Heat the reaction mixture for 10 to 15 minutes in a hot water bath at about 50 degrees Celsius. Pour the reaction mixture in a beaker containing aqueous sodium carbonate solution, and this is to neutralize the excess sulfuric acid and excess carboxylic acid. Sweet smell of the substance formed indicate the presence of carboxyl functional group in the compound. So we take about 1 ml of this is the organic compound, and to that we are adding ethanol. After that, we add a few drops of concentrated sulfuric acid. Now heat the mixture on a water bath for about 10 to 15 minutes. Now cool the solution and it is poured into a beaker containing aqueous sodium carbonate solution. Now just smell the beaker. A sweet smell can be experienced, and the sweet smell is due to the formation of ester RCOH plus R-OH. This is the alcohol. So this is the ester form. Now we will study the reactions of amino group. Organic compounds containing amino groups are basic in nature, so they easily react with acids to form salts, which are soluble in water. Both aliphatic and aromatic amines are classified into three categories. One, primary amine, secondary amine, and tertiary amines. The classification is based on the number of hydrogen atoms attached to the nitrogen atom. First, let us consider the solubility test. To about 1 ml of the organic compound, add a few drops of dilute HCl. Shake well. If it dissolves, it shows the presence of an amine. For example, take aniline, about 1 ml of the aniline test tube. To that, we are adding few drops of dilute hydrochloric acid. We shake it well. It dissolves due to the formation of soluble salt. Aniline plus HCl, we get this compound. An important test for both aliphatic and aromatic primary amines is the carboxylamine test. The amine is heated with chloroform in presence of alcoholic potassium hydroxide solution. To 2-3 drops of the given compound, add 2-3 drops of chloroform and equal volume of 0.5 molar alcoholic potassium hydroxide. Warm the solution gently. A foul-smelling gas confirms the presence of primary amine. The gas formed is carboxylamine, which is highly poisonous. Since it is highly poisonous, do not inhale the vapors. It should be destroyed immediately by adding concentrated HCl and flushing into the sink. So we take the organic compound. To that we are adding chloroform. This is chloroform. And after that we add alcoholic potassium hydroxide. That is potassium hydroxide dissolved in alcohol. After that, gently warm the mixture on a water bath for some time. Now we get the foul smelling gas and we should destroy it immediately. So a primary amine, chloroform, alcoholic potassium hydroxide, and this compound is carboxylamine. The confirmatory test for primary amine is the Aldehyde test. Primary amines, for example aniline, reacts with the nitrous acid to produce diazonium salts. The nitrous acid is generated within the reaction medium by the reaction between sodium nitrate and HCl at about 0 to 5 degrees Celsius. This couples with beta naphthol to give a scarlet red dye which is sparingly soluble in water. So for doing the test, first dissolve about 0.2 gram of the compound in 2 ml dilute HCl in a test tube. And we cool the test tube in an ice bath. To the ice cold solution, we add 2 ml of 2.5% cold aqueous sodium nitrite solution. Now dissolve 0.2 gram of beta naphthol in dilute sodium hydroxide solution in a small beaker. Add the disonium chloride prepared in the second step into the cold beta-naphthol solution slowly with the stirring. Formation of scarlet red dye confirms the presence of aromatic primary amine. So we dissolve the organic compound in 2 ml of dilute HCl. Now we place it in an ice bath. Now we prepare a 2.5% cold aqueous sodium nitrate solution. So we keep the sodium nitrate also in the ice bath. Now we add sodium nitrate solution drop by drop to the test tube. Now beta-naphthol, we dissolve beta-naphthol in dilute sodium hydroxide and a solution of beta-naphthol is prepared. That also is placed in the ice bath. Now we take the contents of the test tube and pour it into the beta-naphthol solution. And if we remove it from the ice bath, we'll observe the formation of a red dye. The reaction can be represented like this. So aniline and reacts with the sodium nitrate and HCl at about 0 to 5 degrees Celsius. And we get benzene disonium chloride. And the benzene disonium chloride now couples with the beta-naphthol. And this is the scarlet red dye, beta-naphthol azo dye.